chromosome. Okay, so if you had a white-eyed female, then that means she has to have 2 copies because it's recessive. She's got to have 2 copies. If you had a red-eyed male, he only has the regular big R, okay? Now, if we cross these two, we would know it was sex-linked if all the males ended up with white eyes. Why? Because the only way the males can receive their X is from their mom. They have to get their Y from their dad. So we would say that eye color is a sex-linked trait found on the X chromosome. Okay, so red eyes and red eyes, both the heterozygote and the homozygote dominant express red eyes. Only the recessive will express the white eyes, okay? When you do sex-linked traits and you draw your Punnett square, you're going to need to get used to drawing your Punnett square where you have the X and the Y. And this is only for sex-linked traits because then you guys get really excited and start drawing all your Punnett squares with X and Ys. Doesn't matter for autosomal traits, but for sex-linked traits, you want to make sure that you have your X and your Y. And if it's carried on the X chromosome, you show it on the X chromosome. And this is why only if all the males were to show a white eye color, that would be an indication of it being a sex-linked trait. Because if you look here, oh, I guess that's not filled in. I thought that was going to fill in for us. If you look here and you draw your square, what you're going to end up with on your square, and I'll just go ahead and draw it out, is the females get the dad's good version, the big R, but the males, and I mean it's all relative, but the males get only mom's copy because that's the only X they can get. So all the males, the little R indicates the white eyes, would have white eyes, and all the females will have red eyes because the heterozygote can be is expressed as red eyes. Okay, this is showing you the square filled out. And again, you can tell that this is sex-linked because all this, in this case, the dad, if we're going to reverse this, the dad has the white eyes. So look how things will change, okay? Now, if dad had white eyes, well, mom is a homozygote red-eyed, then everybody's going to be okay because mom's going to give her good red eyes to the boys, and she's going to have one X to give to the girls, and the girls are also going to get the white-eyed X from their dad, but the mom has red eyes, so the girls end up expressing as red eyes, okay? So these are the ways you need to look at Punnett squares to try to determine the mode of heredity. Okay, so again, sex-linked, here's your definition again, are traits that are coded for by the alleles on the sex chromosomes. Okay, there's your basic definition that you're gonna have to know for your test. When we say it's an X-linked, the genes are found on the X chromosomes. When you say it's Y-linked, the genes are found on the Y chromosomes. Since the X chromosome is larger, we have a lot of times we'll have more X-linked traits. Okay, this just shows you some of the various traits that are found on the X chromosome. And then you see there's only a couple found on the Y. Sex-linked traits, males, again, this is just explaining what I talked about, only have one X. We say, and this is a word you need to know, we say that males are hemizygous. That means hemizygous means they only have one X. Therefore, a male who carries the recessive allele will show it, they'll show the X-linked trait, okay? And that's why, because males are hemizygous, get used to that word, that is the reason why we see sex-linked traits that are recessive appearing more frequently in the males. Okay, this is a great example where you could say, okay, looking at this pedigree chart, is this disorder autosomal recessive or sex-linked? If you look here, This would be the affected. The mom is affected, okay? So that means, let's say it's two little r's, okay? And this would be the dad, and the male is not affected. If we look here, we see that the female, the daughter of this, you have two daughters and a male. The male is affected and the female is affected. Well, that kind of makes me think, okay, well, she could have gotten the affected. If dad isn't affected, she has to get one X from her dad, right? So to be affected and be a sex-linked recessive, then she would need to have a faulty X from her dad and a faulty X from her mom. So that makes me think this is not sex-linked. But we're going to look at this a little bit more because because dad can't be a carrier, right? So that kind of makes me think, if dad can't be a carrier, then this is probably not sex-linked. And again, the male here is not affected. So she got a good one from her dad. So if you look here at this dad, this one makes me kind of question it a little. Because he gives his X to his girls, right? So all the girls got it. Mom could have a faulty X, but then that would mean that the girls you'd have at least one of them popping up in the girls if this was a sex-linked trait. So I'm going to say this is not a sex-linked trait. Okay. Red and green color blindness in humans is caused by a sex-linked recessive allele. A colorblind man marries a woman with normal vision whose father was colorblind. The couple has a son. What is the probability that he's colorblind? Well, let's think. The colorblind man marries a colorblind woman. So let's make colorblind an easy way. Let's call it T because that's easy to see. So in order to express colorblindness, you need two little t's because it's a sex-linked recessive. But the mom is normal vision whose father was colorblind. So that tells me that mom has to look like this. Big X or big T from that's why she's not colorblind, and a little t that she got from her dad. The dad, or her husband, I should say, of this match, has to have a little t because he's colorblind. So the couple has a son. This is one of those tricky worded AP questions. They want to know what is the probability that he is colorblind. Well, if we look at the son, so now we're kind of reducing this to only looking at the son, right? So you have a 50% chance of having a son, right? And what is the probability that the son would be colorblind? Well, of the two boys, what's your chance? 50% chance that the boy would be colorblind. Okay, now out of all of the progeny, you'd have 1/4 chance of having a boy that's colorblind. Okay, all right. We have two more questions that, again, you could pause and answer it yourself and then come back. These are going to be questions on your test. When Thomas Hunt crossed the red-eyed F1 generation flies to each other, the F2 generation included both red and white-eyed flies. All the white-eyed flies were males. What was the explanation for this result? Now remember, when we looked back at the first cross, he crossed red-eyed flies to each other. The F2 had red and white flies, but all the white flies were males. So that means that you must have had a red-eyed female that was a carrier of the white eyes. And the males, the females, must have gotten, for the original cross, all the males must have been red-eyed because it says they were all red-eyed here, the F1 generation. So all the males looked like this. They had a big R. So all the males look like this in this cross. And the females must have looked like this. Oh, oops. So the males must have looked like this and the females must have looked like this. If you cross these two, some of the males will inherit mom's little R, which is the white eyes. None of the females, even if they inherit this little R, will express white eyes because dad is always going to give them their red-eyed gene. All right, we've got one more example. In birds, sex is determined by, now birds are different, a ZW chromosome. Males are ZZ, females are ZW. A recessive lethal allele that causes the death of the embryo is sometimes present on the Z chromosome in pigeons. What would be the living, and this is tricky, check that out, living sex ratio in the offspring of a cross between a male that is a heterozygote for the lethal gene and a normal female? This is a tricky one because we just get stuck on humans, that XY is a male and XX is a female. Now we have the reverse going on with birds, and this is true. So let's look at this cross. We have, we have a male that is heterozygous for the lethal gene. So that's ZZ, and that's why he gets to live. So I'm going to make the lethal gene a little l, and the regular gene a capital L. And so he's heterozygous, so he's got one good gene. The female is alive, so she's got to have one good gene, and it's only found on the L. So she's got to look like this. So this here is the female with the non-lethal gene, or I made it a capital L. And here is the male, and I'll put a star by the lowercase l. And here he is with his one lethal gene and his one good gene. Now that gene is only on the Z, so, and it takes 2 for it to be lethal. So I'm going to go ahead and fill this Punnett square in. And obviously, if you look, all the males are going to get at least one good copy from their mom. So they're not going to have any, if you look here, any of the male offspring having actually dying. Okay? Here's the male offspring right here, ZZ. Okay? You're not going to have any of them dying. But if you look here, here's the female. You're going to have one of the females dying and one of the females inheriting the good gene. That would be the capital L. So this wants to know what would be the living sex ratio in the offspring of a cross between a male that is heterozygous for the lethal allele and a normal female. So your living sex ratio would be, you have 2 males to 1 female. That's your sex ratio, right? Because this female doesn't live. Okay? Hopefully that helps. All right. Well, this was a lot of talk. Hopefully you understand how genetics works beyond Mendel. You'll be able to tackle that worksheet. Thank you guys so much.